Welcome to the 34th International Materials Research Congress, IMRC 2026. Today, I'm thrilled to present an explainer on a really fascinating breakthrough in two-dimensional materials. We're going to dive into a study titled Tuning the Electronic Properties of 2D IAL and AU-MG Bimetallic Systems via Density Functional Theory. So, if you're interested in the frontier of materials science and how we can radically alter material behavior at the atomic level, you are absolutely in the right place.
Okay, let's briefly look at our agenda for today. We'll start with an introduction, outline our computational methodology, explore the electronic and mechanical properties, and finally wrap up with our conclusions.
All right, part 1, introduction. Let's talk about the objective of bimetallization. Our baseline material today is Goldene. It's pretty amazing when you think about it, taking a heavy noble metal like gold and stabilizing it into a single atom-thick 2D sheet. But what happens when we tweak that pristine baseline? Our main objective here is to figure out exactly how bimetallic alloying, specifically incorporating aluminum to create AuL and magnesium to create AU-MG, modifies the structural, electronic, and mechanical properties of this unique two-dimensional system.
Moving right along to part 2, computational methodology, which is driven by density functional theory.
To get a truly accurate picture of how these materials behave at the atomic scale, we relied on density functional theory, or DFT. Specifically, we used the Siesta computational code to establish a very rigorous, self-consistent framework. We set a mesh cutoff energy of 200 Ri and used 41 independent K-points in the Brillouin zone. Now, those aren't just arbitrary figures. They were meticulously chosen to guarantee high accuracy and numerical convergence throughout the simulation. We also ran precise strain energy calculations to evaluate the mechanical properties, which we'll look at in just a moment.
Next up is part 3, electronic properties, focusing on the transition to metallic behavior. To start, pristine Goldene behaves as an indirect bandgap semiconductor, and it has a calculated gap of exactly 2.93 electron volts. That's our starting point. But here's where it gets really exciting. When you incorporate aluminum or magnesium, that gap collapses entirely. Through this bimetallization process, both systems undergo a complete transition, shifting away from being semiconductors and moving into a purely metallic state. It's a massive modification of the base electronic structure.
But what's really fascinating is how they achieve that metallic state, because it's quite different for each. In the AAL system, the material actually preserves partially linear band dispersions right near the Fermi level. This is a great indicator of highly mobile charge carriers. On the flip side, the AU-MG system gets there through strong hybridization between the d and s orbitals. This hybridization creates a much higher density of states around the Fermi energy, giving it a significantly more pronounced metallic character.
That brings us to part 4, mechanical properties, where we weigh rigidity against flexibility.
So we know how the electronic profile shifts, but how do these materials hold up physically? If we look at the Young's modulus derived from our strain energy calculations, the contrast is night and day. The AuL system is incredibly stiff, sitting at a highly rigid 256.59 newtons per meter. Adding aluminum basically turns this material into microscopic armor. But look at AU-MG. It drops all the way down to 36.54 newtons per meter. This promotes a highly flexible structure that behaves much more like a malleable sheet. It's a huge mechanical trade-off, driven entirely by which metal we choose to alloy with. Finally, let's wrap up with part 5, conclusions on tunability and future applications.
So what is the major takeaway here? Basically, this first principles study proves that bimetallization is a phenomenally powerful tool. We can effectively tune the electronic and mechanical properties of Goldene, completely erasing that 293 electron volt band gap to push it toward a metallic state. We can also dictate whether the material acts as a rigid shield or a flexible sheet through targeted mechanical design. And crucially, we can achieve all of this while completely maintaining the structural stability of its underlying hexagonal lattice.
This kind of unparalleled tunability makes these bimetallic systems prime candidates for next-generation nanoelectronics, flexible devices, and advanced functional materials where you need highly controllable conductivity and a tailored mechanical response. It really makes you wonder, if we can control Goldene this precisely, what other 2D materials are just waiting to have their limits rewritten? Thank you for your attention.